All right, we are on a chapter that I really enjoy called Kinetics, and this chapter deals with the speed of reaction. So we talked about in a previous chapter whether a reaction will occur or not spontaneously, or what we called favorably. But we said that that did not mean that it occurred quickly. And so in this chapter we are going to talk about what influences the rate or the speed at which a reaction occurs. How can we calculate that rate, and how can we compare it to the rates at which other reactions are occurring? So we'll just start off talking about the basics, reaction rates. So kinetics is the study of reaction rates. So when we talk about kinetics, we're talking about how quickly a reaction will go. The rate of a reaction can be viewed three ways, and it's kind of like, say a person is standing in the middle of the room and you walk around them, or a statue even, or a piece of art, and you view it from three different directions. You're viewing the same thing, but we're just talking about it in three different ways. So when we talk about these three different rates, they are speaking of the same thing, but just in different terms. So the first way that we can talk about the rate of a reaction is we can talk about the rate at which the reactants are disappearing. So if the reaction is moving forward, which we'll assume that it is when we're talking about kinetics, the rate at which those reactants are disappearing is one way that we can talk about the rate. We can also talk about the rate at which, of course, the products are appearing. So in that manner, they're going to be opposite in sign, right? Because the reactants are disappearing while the products are appearing. And then we can talk about the rate at just which the overall reaction proceeds. And so that is going to be a little bit different in terms of the way that we calculate that, because we're going to talk about the reaction as a whole. So disappearance or appearance of reactants and products, or just the overall reaction as a whole, and we'll talk about each of those individually. Every single one of these is found by looking at how the concentration changes over a period of time. But how we calculate them and the units we use, etc., is going to be specific to which of these that we're talking about. All right, so first let's look at the rate of disappearance of a single reactant. So we have a reaction that we're discussing, and it's written above, just a generic reaction. A plus B yields D plus E. So we could isolate and say, okay, let's talk about this reaction in terms of the rate at which A disappears. And so for that, we would say, okay, the rate at which A disappears is going to be equal to the change in concentration of A. That's what that triangle always means. So that would be the final concentration of A minus the initial concentration of A, divided by the change in time over which this occurred. So we know about rates from our car, right? We have miles per hour. That's a rate. How many miles did you go and how long did it take you? That's your miles per hour. Same thing with a reaction. How much did your concentration change and how long did it take it to change? Concentration change over time change. So the concentration change for any reactant is going to be negative, but our rates are always positive. Okay, rates are always positive. So your change in concentration is negative, then the negative sign there is just there to make your rate positive. So this right here, this change in concentration will be negative, and a negative, that's going to make it positive. You could do the same thing with B as your reactant. It's going to have the same rate as A because they're being used one at a time according to our coefficients, and your equation would be the same. The negative change in B, since B is decreasing, over your time is equal to your rate of B. You can also talk about the rate of appearance of a product, and it works the same way. The only difference is you don't need a negative sign because your change for any product is going to be positive if we assume, which we will when we're talking about kinetics, we're going to assume that our reaction is moving forward. So the concentration change of your product divided by the time over which that occurred would be the rate of that product in the reaction. And again, your rates are always positive. When you're talking about a reactant, the change in concentration is negative, so we have that negative sign so that the rate comes out to be positive overall. The rate at which one species appears or disappears can be used to find the other rates. For example, if we know the rate at which A appears or disappears, in this case it would be disappears, we could use that to find the rate at which B disappears. Or we could use that to find the rate at which D appears or the rate at which E appears. Now this at the bottom has always been somewhat confusing to me. So I just like to think of it in terms of stoichiometry. If I know the rate for A, let's say A has a coefficient of 1, and D has a coefficient of 2. If I know the rate for A and I want to find the rate for D, I'm just going to use the ratio. There are 2 D's which are appearing for every 1 A that is disappearing. Okay, and you're just using your coefficients to make this ratio. If you know the ratio for B, let's say B has a coefficient of 3 and E has a coefficient of 5. If you know the rate for B and you want to find the rate for E, well, you'll just use the ratio. There's going to be 5 E's made for every 3 B's that are lost. They really like to pose this question. We'll see it on our test, on our homework, on the AP exam if you take it. They'll give you the rate for one of these and they'll need you to find the rate for another. So if you know the rate for whatever, let's say you know the rate for B in this case, and you want to find the rate for something else, you put the one that you're looking for on the top with its coefficient, the one you're trying to get rid of on the bottom with its coefficient, and you just do the math. We're simply using our stoichiometric, our mole-to-mole, our balanced equation ratios in terms of rates. So you can use your ratios and your rates to find the rate for something else. All right, let's look at some graphs now. So let's say we have NO, which is what we're talking about here, and we have no NO at the beginning, and we're making some NO because it's a product, and this is a single arrow reaction, so we're assuming that this reaction is just moving forward. So over time, our NO concentration is going up, and then it starts to flatline, which we can assume means that we're not making any more because we're running out of this NO2. You could also think about it as equilibrium. This is not a double arrow reaction, so it's more likely that we're running out of this reactant. All right, but the point here is that our concentration, look how quickly it goes up in the beginning. I mean, in the beginning, that concentration is changing very quickly. And then it kind of starts to level off. And then up here, it's not really changing at all. Or we could say that the change is 0. So if you wanted to find what is called the instantaneous rate, what is the speed at that moment? Think about when you're driving your car. You kind of have an average speed over which you travel. But if you want to know the speed at that moment, you look at your speedometer. The same thing is true for a reaction. Reaction speeds change. They usually start out really fast. So in the beginning, they're usually moving a lot faster, and we'll talk about why. And at the end, they're usually moving much slower. But if you want to know the rate at some moment, let's say this is 5 minutes. And I want to know how fast is this reaction going at 5 minutes, right there. How fast is it going? To do that, I can't take the change in concentration and divide it by the time, right? That's how we said earlier that you find the rate. Change in concentration of NO over time. That would give me an average. If I did change in concentration over change in time, that would be an average. But I want to know how fast is it going right now, this minute. So to do that, you make a tangent line along your curve, and then you find the slope of that tangent line. Now remember, slope from math is equal to change in y over change in x for that line that you've drawn. Right? So the key here is that if you want to find the rate at a particular time, not the average, but the rate at a particular time, you need to draw a tangent line at that time along the curve and then find its slope. What they often ask you to do here is to describe what you would do or to draw the line. So you need to be familiar with drawing tangent lines. So let's go down here. What if I want to know the rate at this point right here? Let's say this is 1 minute. Then I would draw a tangent line at 1 minute and find the slope of that line. You can see, though, that the slope of that line, the steepness of that line, is much greater than the slope of this line. And let's say we want to find the speed at this time. Maybe this is like 12 minutes. Draw a tangent line right there. Notice that's much flatter. So as the reaction proceeds, the speed or the slope is decreasing. And that's your instantaneous speed. All right, now let's look at these other two that they've now drawn on the graph. Here we have our O2, which also started at 0 because it was one of our products. And it is increasing as we go. And again, if we wanted to find the rate at any time, we would just find the slope along that tangent. Now, what do we notice about O2 versus NO? We are making a lot more NO than O2, right? How much more? How much more NO are we making than we're making O2? We are making twice as much. If we look at the slope, any point along these lines, the NO slope is going to be twice as big, and that's all based on this coefficient. The NO2 concentration is decreasing, getting closer and closer and closer to 0. I don't know if it'll ever reach 0, but it's getting closer and closer. And the NO2 line, you'll notice, is a direct mirror of which of these? It is a direct mirror of the NO line because they have the same coefficient. So as this goes down by 2, this goes up by 2. Down by 2, up by 2. However, this goes down by 2, this goes up by only 1, the oxygen. So they do not have the same graph. But the NO2 and the NO, because their coefficients are the same, their graphs mirror one another. As one goes up, the other one goes down at exactly the same amount. For a reactant, as it goes down, you would still find the tangent line if you wanted to know how fast it was going at any point. But notice your slope would be negative, and your rate is never negative. So your rate is equal to negative that slope. And that negative sign is just there for the reactant so that our rate will be positive, because the slope, as you can see there, is negative. All right, so on these graphs, you need to be able to find the instantaneous rate. You also need to be able to label these. So what they'll do sometimes, they'll give you a graph like this, and they won't put anything on there. You got to figure out what everything is. Well, you know your reactants are going to be going up, so you can label those. You know that the one with the bigger coefficient is going to go up more than the smaller coefficient. And then, if two things have the same coefficient, they should be mirrors of each other if one's a reactant and one is a product. All right, let's look at rate a different way. So here's a reaction, and we have time 0 and then time 60. And in here at the beginning, you see we have 15 moles, and we'll just say this is 1 liter. So 15 molarity of our AB, and then it reacts. After 60 seconds, we only have 5 of those left. All right, so if we had 15 of these to start, and now we have 5, what is that change in concentration? That's a change of 10, right? And it went down by 10. So you'd say negative, because it's a reactant, and then it went down by 10. So negative 10 molarity divided by how much time went by. That was a change in time of 60 seconds. Okay, so our rate for this reaction is 10 divided by 60. So that's 0.17 molarity over seconds. Now the units are usually easy to figure out on these problems as long as you include your units in your math. So we had molarity on the top and seconds on the bottom, so our rate is molarity per second. Now this is the rate for which of these? This is only the rate for AB. The rate for A and B as our products is different because they have different coefficients. So let's calculate it down here and see how they relate. A and B both change by 5 molarity. And they're products, so their change is positive. Let's go on the top. And it's still over 60 seconds. So we have 5 divided by 60 is 0.083. And that is molarity over seconds. Now if you look at those values, 0.083 within significant figures is half of 0.187 because A and B's coefficient is half of AB's. So if you know one rate, you can find the others. For example, I know that A2 and B2 have to have the same rate because they're being made 1 and 1. And I know their rate is half as much as AB because AB is being used 2 at a time. Right? So that's how we can use this sort of information to find rate. It's the change divided by the time. And really they could just give us one of these and we could find all of the others. So there's that information again. You have the rate of disappearance of your reactants will have a negative sign so that it comes out to be positive, and the rate of your appearance is already positive. And then you can find the rate of something else by comparing it to the others. For example, the rate of A we know is going to be half the rate of AB because A has a coefficient of 1 while AB has a coefficient of 2. Right, so we'll stop there, and then next time we'll talk about the rate for the overall reaction, which is known as the rate law.